It also is kind of a unit 12. We're going to take 4 days to review algebra before you take algebra again. We have to kind of switch your minds back to that just a little bit more. You know what I'm talking about? We've been doing algebra all the time, but not at the intensity that you're used to anymore. So we're going to do a review so you're not coming back into full shock next year in Algebra 2. But here's the hard thing about Unit 11. You've never seen most of this stuff before at all. That means you're going to have to learn the notes and learn them well and review constantly through this. And it's the last big chance of raising your grade before the final. There's only one more test. We have like 3 quizzes. We've had so many quizzes this semester, they're not going to bump your grade that much as a test, right? So we need to make sure we're staying on top of those things. Are you guys with me on that? Can you give me focus? Can you follow along and give it full effort, right? All right. So let's do some quick review of some things that you should know. First of all, everyone should remember way back from unit, was it 8 or 9? I can't remember. That talked about the definition of a circle. All right. Remember, a circle is a set of all points in a plane the same distance away from the center. And we always name a circle by its center point. And remember, the symbol that you use is literally a circle with the center point. So we don't just, change it to an O or a 0 by accident. So we'd call it like circle C or circle Z, whatever that center point location is. Also, when we're working with circles, location or how you refer to things are really huge. So when I have a circle, I need to remember that anything inside of it is still interior, which doesn't, that makes sense, right? The interior of a circle. Then we have anything on the outside of it is the exterior points of the circle. But what do I call a point that's located right there? It's not a point of tangency because there's no tangent. What's it going to be? That's a point on the circle. It's on the circle. There's a difference. Outside, inside, and on. Location really matters when you describe things with circles. Are you guys with me on that? All right. So then we're going to sit there and we're going to describe a few things you've had a little bit before, but most of the stuff you haven't. Okay? So with this first one here, we have the word chord, and this is one you've probably had somewhere in middle school that you talked about. What is a chord? And I don't mean a musical note, okay? A chord in circle terms is just first of all, a line segment, which means it has a beginning and an end. Its beginning and end are on the circle itself. So you can have an infinite number of chords drawn in a circle. And so you could have, like, for instance, segment AB in that diagram to the right is considered a chord. It stops and ends on the circle. Both of them have to, or it doesn't work. Now, here's my question for you. What is the longest chord of a circle? What is it? It's the diameter, right? Think about it. If I have a circle here, and I have its center, what's the farthest I can get away from each other is if I go right through the center, right? So remember, a chord, let's just go it this way. Diameter is the longest chord, really, that you can have. Does that make sense? So is a chord technically a diameter? No, a diameter is technically a what? A chord. So chords don't have to be diameters, but all diameters are chords. I think of it like that. All right, next one we have what's called a secant line. And we use that terminology a lot. Oh, I can't even talk right now, sorry. Terminology a lot in calculus. A secant, first of all, is a line, not a line segment, it's a line that intersects a circle at 2 points. So basically, think of it as like you start with a chord and then you go outside the circle. All right, so like right here when you see with line L, do you agree with me? This segment from here to here is a chord, right? But what does the secant do? Keeps on going. So like you see where my thumbs are right here. This would be the chord. This is going to be the secant. Are you guys with me on that? It just basically shoots through. Has to touch it in 2 spots when you're working with it. So in this case, that's going to be your line L. All right, I need to make sure I go on tablet mode here. All right, now, next one, we have what's called your tangent. A tangent is a line in the same plane as the circle that intersects it at exactly one point. So the key thing, it has to be in the same plane. But like off to the right here, you see it's that green line. That's going to be line M is a tangent line. Notice it looks like the circle's just resting on it. Or if I drew it somewhere else, it looks like the line is resting on the circle. Are you done? Okay. So with that, you can have an infinite number of tangent lines to a circle, but it can still only intersect at one single point. That point has a name, and as you see it labeled there, it's called the point of tangency. And again, that helps us talk about location of things. In this case, that would be point C in our diagram. Now, think of tangent lines as pretty easy. Since I can't go through the circle and I only can touch at one spot, think about when you hear a person telling a story, right? They start telling a story and they go, oh yeah, that reminds me of this. And then they go on a what? Tangent. Goes away from the circle. Doesn't that tangent line look like I touch it, now I'm going away from it now? So it's the same type of idea. That point of tangent is actually very helpful. All right, so now let's go with this one here. And it says, identify each line or segment that intersects circle L. So that means our center is what point? L. So it makes it really simple for us. We know it's point L. All right, so when we're doing this, let's just go through everything that we've just learned. For instance, I should be able to name some chords from this. All right, so I want to know any chords that you might have. Does anyone name a chord for me? All right, so it'd be segment JM. Remember, chords have to be line segments and their endpoints have to be on the circle. Is there any other ones? Yep, be segment KM. Excellent. Right? Does it, as segment KM, is both of its endpoints on the circle? Yeah, that makes it a chord. Well, that also makes it a what? A diameter. So segment KM is also a diameter in this case. Remember the longest chord. All right, do I have a secant line when I'm doing this? Do I have one that keeps on going? What? Yeah, and that would be, here's where the notation is huge. You have to tell me it's line JM or I wouldn't give you credit for that. If you said segment JM, I'd be like, nope. You already told me it's a chord. A secant has to go a line that goes all the way through and keeps on going. All right, then we have a tangent. What would be your tangent in this case? Yeah, it would be line M. Excellent. So it'd be line M. A few of you might have in your head said line HM, but if it's a lowercase letter, can I use it for a point? Remember, when you name a line, it has to be 2 points on the actual line itself. Now, point of tangency in this case, they didn't ask for that. That would be point H, correct? Now, there's a couple other things that are still intersecting the circle that we haven't talked about yet. We already should know these. How about the radii of the circle? Do they intersect the circle at one point? Yeah, so what are the radii of the circle? I heard it, segment J, segment JL. What other segments? Yeah, segment KL. What other one? Segment ML. All of those are things that you should be able to identify from circle L. All right, flip the page over. Your turn. Go for it. See how you guys do. What are going to be your chords? Does anyone say segment QR? All right, so it's segment QR. What was the other one? ST? All right, so segment ST. Awesome. Okay, how about a diameter? Yep, segment ST. Awesome. How about a secant? Very good. Line ST. Just a little bit of difference, isn't there? And then we have a tangent. What did you guys get for a tangent? Remember, those are both capital letters, so you have to name it with 2 points. So it'd be line what? UV. What's your point of tangency for that? Point U. All right, what's the radii for this? QP, SP, and which one? TP. All right, You have to do that for a couple homework problems tonight. Are you guys good? You think you could do it? All right. Be careful with your notation. Make sure you have lines when you should have lines, line segments when you have line segments. All right, now the first two up there should be quick reviews from when we talked about circles before, right? When we talked about areas of circles. We talked about what makes circles congruent. They have congruent radii. They can be in different planes and universes for all we care, but as long as the circle has congruent radii, they're congruent. Concentric circles, remember that's like your Target brand symbol. They all are in the same plane and they share the same center. So we got concentric circles. Now we have one that are called tangent circles, all right? So two coplanar circles that intersect at exactly one point are called tangent circles. Now with that, we can talk about them a little bit more. We call them as externally tangent, and we also call them internally tangent circles. Now, obviously, the one that says internally tangent circle, one circle is inside the other, isn't it? And externally tangent circles, they're both outside of each other. They only have that one point in common. All right, so that's terminology you just have to know for problems like the next two problems. It says on here, find the length of each radius, identify the point of tangency, and write the equation of the tangent line at this point. Now, guys, keep this as simple as it's supposed to be, okay? When I talk about the radius of circle S, what's the length of the radius of circle S? What is it? Guys, look at the diameter if you have to. What's the diameter? Isn't the diameter 3? So what's your radius going to be? 3 over 2? Okay, great. Good enough. 3 over 2. What's your radius of circle R? What do we got? Isn't that 2? Use the diagram to help you. So the radius is going to be in 2 units. Now, I want to know the point of tangency for this. Now, if I'm doing a point of tangency and there is not a point, a letter to tell me what it is, don't I have to use the ordered pair? Guys, what's your ordered pair for where they intersect at? Negative what? A lot of you said 0, 2. But guys, isn't it negative 2, 0? Don't we have to do the x first, then the y? All right, so that's my point of tangency. Now we're to the next point. I need to be able to get here. I want to know the equation of this. Now, before you completely panic, remember we did learn this year, okay? So when we talk about the equation of the tangent line, we're just using what you learned way back in, get this, chapter 3. Okay, so we talked about the equations of circles. Now, what are the two things that you need for an equation of, equations of circles, equation of lines is what I meant to say. Equations of lines. Don't I need to know the slope and don't I need to know a point? Guys, what's the slope of this line? It's 0 because it's a horizontal line, right? So the slope of it's 0 because it's a horizontal line. Now, isn't the point I'm going to use just going to be negative 2, 0? Can't I use point slope form? Because remember, point slope form is y minus y1 equals m times the quantity x minus x1. I'm just going to plug in, this would be your x1, this would be your y1, your values. So I get y minus 0 equals 0 times the quantity x, subtracting in a negative 2 makes it what? Positive 2. That's good enough. If you remember the shortcut way, a horizontal line is only equal to what its y-intercept is. You could have also said y is equal to 0. But I think for most of you, I would just stick with the point slope form. Now, what's hard about that is if you did it with a vertical line, then you can't use point slope form. Otherwise, horizontal or any other type, you could easily do that. Are you guys with me on that? Hopefully that reviewed. It wasn't meant to be hard, but just to review that with you. All right, let's do another one. Guys, what's the radius of circle D? Yeah, that's just 1, 2, 3, right?
So the radius is 3. I want to get the radius of circle C. Guys, what's that radius? Yeah, that's just 1. So that'd be 1 unit. Do I have everyone with me so far? Because I'm going fairly fast. Okay. Next page. All right. So what do you got here? Point of tangency. What's my ordered pair for this? Guys, what's your ordered pair? 2, -1. Perfect. Now, this lovely line is my tangent line once again for those 2 circles. So if I'm looking for the equation of the tangent line, what's my slope? The slope is 0. Is that my point right there? Can I use point slope form? As long as I have the slope and I have a point, I can use points form. So I get y minus y1 equals m times quantity x minus x1. So I get y, subtracting a -1 makes it what? Positive. Then I have my 0 and I get my x minus 2. So this, do you think that's good enough for me? Now, the only other answer I would accept with that would be y equals a -1. Would also work. Either one of those 2. Guys, use these as your guide when you're doing your homework tonight, okay? Make sense? All right. Now, new term, but not a surprising term. It's called a common tangent. All right, a common tangent. Make sure I can spell it here a little bit more. Actually, it should be an O, and I keep putting an A in there. No wonder why it didn't make sense. A common tangent is a line that is tangent to 2 circles. So basically, it's a tangent line for both of them. Notice the first set right here. These are called external tangents, and they look like they're just resting on the bottom or on the top of the 2. The ones to the right are called internal tangents. I can't talk today for some reason. I struggles this period. Are common internal tangents, and the reason why they call them internal is they cross between the line segment that connects the 2 centers. That's the term that they use for that. So again, notice they still intersect the circles when you're working with it. Why? Well, this is going to be some stuff that we're going to apply. We're going to be applying some tangent stuff. So I'm going to give you the theorems, and then I'm going to go back up and mark up the diagrams that you see above. Okay? So these are just some theorems about tangent lines. So the first one is, if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So basically, I can draw, because we have an infinite number of right on a circle, right? So I can draw a radius in about anywhere on on a circle. So in this case, I would always draw it to the point of tangency, and I would form a giant right angle. So the key thing that anytime you see a tangent line and a radius, you're going to mark in the right angle. So here's my thing. Always mark diagram. It always helps. Now, look what I mean by what up above is, okay? Looking at those 2. Guys, if I have circle A, can I draw the radius to the point of tangency right here? If I do that, what type of angle is being formed? Right angle. Circle B to the point of tangency. Can I form a right angle right there? How about going down? Couldn't I do the same thing? And the answer is, yep, the same thing could happen. Same type of idea when you have internal common tangents. Because when I look at this, one of the top things they'll do is they will always like connect the centers of the 2 circles. But then notice what I'm doing here. I'm going to draw selectively radii to the point of tangency. If I do this and I'm using my theorem, I know they're going to be perpendicular. Now guys, I want you to look carefully at these 2 triangles right here and here. What do you know about those 2 triangles as a result? Just start talking to me what you know. I'll probably come to you pretty quick. They're similar. Exactly. They're similar to each other. And here's the reason why. You guys see the pair of vertical angles right there? Don't I have a theorem that says AA similarity for triangles? If I have two pairs of congruent angles, do I have similar triangles? So yeah, those two triangles that you see highlighted right there, they're going to be similar to each other. Notice they didn't have this big cool theorem about it. You're just supposed to know how to draw in the radii, first of all, and you're supposed to remember your similarity stuff. That was way back in chapter 7. If I were you, I would be looking over chapter 6 and chapter 7 because those were so long ago. I mean, that's January and February. You can't tell me you remember those off the top of your head. It'd be time to start reviewing. All right. Now, the next one is just the converse of the previous stuff. All right, so just the converse. If a line is perpendicular to a radius of a circle at the point on the circle, then the line is tangent to the circle. So this one's just going the other way around. So saying, hey, look, this line and radius are perpendicular. Oh, so it must be a tangent one. So it's just going the other way. Watch me if I destroyed my pen by doing that. No. All right. So make sense? So let's crank these out, guys. All right. And we do have to do, in the next 20 minutes, we have to do a lot of problems. Are you guys ready? I think you can do it, but you're going to have to stay with me. Are you all awake? Good. All right. First one's first. Early in its flight, the Apollo 11 spacecraft orbited Earth at an altitude of 120 miles. That means right there is 120. What was the distance from the spacecraft to the Earth's horizon rounded to the nearest mile? So I want to know the length of segment EH. I'm going to call it X. But notice what they drew. They drew the radius to the point of tangency, and isn't there a nice, lovely little right angle drawn in there? Right there, correct? Now, they're like, okay, it's a right triangle. Should we know how to work with right triangles at this point in our math career? Yeah. In fact, though, I'm going to have to use the fact first that the radii of my circle are congruent so I can get the length of segment EC. Because I want the whole segment of segment EC because I need to use that as the hypotenuse of that right triangle. Well, isn't that just going to be 4,120? You guys with me how I got that? All right, great. Well, now let's just use the Pythagorean Theorem. Let's go x squared plus 4,000 squared, because that's leg squared plus leg squared equals hypotenuse squared. Now, we're going to let the calculator do a lot of the work. So can I just subtract that 4,000 squared to the other side? You can let your calculator do that, but I'm going to do it more towards the end. Can someone punch that into their calculator real quick? What's 4,120 squared minus 4,000 squared? Is it 400? Okay, that's what I got. Awesome. Now, guys, are we done yet? No, I still got to take the square root of both sides. And remember, we want to take the plus or minus of both of our square roots. Can I drop the negative, though? Yep. So what do we get approximately to the nearest mile when you guys punch that in? Is everyone in agreement? Those of you that got your calculators working, do you agree? I don't want to take just one person's word for it. Did we get 987? All right. Don't forget, you need to label. So that'd be about the case in this diagram. By the way, this just makes me think of my favorite new movie, Hidden Figures. Great movie out there, guys, about math and science, women in science, segregation. Oh, it's so good. Such a good movie. Done very classy. I'm very impressed. By the way, I actually recommend reading the book. If you're at all science, computer, or math oriented at all, I would read the book. It's very interesting. It's the first time that I ever read a book that was very historical like that. It was nothing really wow and exciting in the book that actually taught me more about segregation in the U.S. in such a good way. Like, you didn't feel beaten either way. Does that make sense? Like, it was just done really well, and to talk about like the role in women in government and government agencies. It was really good. It was just a very good book. All right, now let's apply what we've learned now. Sidebar, that was my tangent for today. Got it? Tangent. All right, yeah. All right, next one. Assume that the line appears to be tangent. Back here to tangent R tangent. Point C is the center of each circle. What's the number one thing I want you to mark in this first diagram? Yeah, I'm gonna, not right triangle, right angle, right? That makes it a right triangle. The radius to the point of tangency right here is gonna make a right angle. As a result, should I be able to solve quickly for x? Yeah, guys, how would I do that? All right, what's confusing? Okay, then let's just do the problem. All right, so when we do this, do you guys agree with me that a triangle still has 180 degrees no matter if it's in a circle or not? So when I do that, subtract the two angles that you know. So that's 180 minus 148. I get that to be 32 degrees. Now, if you remembered that the acute angles of a right triangle are complementary, you could have also gone 90 minus 58, which is also 32 degrees. But here's the thing. I don't want an answers. You still have to show me your what? You got to show me your work. You can punch it into your calculator after that, but you still got to show me how you started with this. Now let's look at the next one. I'm looking for x. Do I have a radius to the point of tangency? In fact, I have two of them, so shouldn't I mark both of those? Talk to me. What would you do now? You know what? You're going to make yourself go through more work. It's not a bad way. That would totally get you the right answer if you remember to double it. What's another way of doing this one? 360, right? Guys, isn't there a quadrilateral drawn here? And am I missing only one side of that one angle of that quadrilateral? Remember, a quad's angles add up to, you don't have to write this down unless you need to remember that, 360 degrees, right? So if I know 3 out of the 4, can't I just go 360 minus the 3 angles that are there? And that ends up being like 360 minus, I think that's 310. And that'd be 50 degrees. Now, I agree with those of you who decided or wanted to go like, can I split this down the middle? Yes, but you're actually making a lot of assumptions you didn't know for certain. The only way that would work is if those two right triangles are congruent. Are those two right triangles congruent? So you're not answering it fast enough for me. They're congruent because of hypotenuse leg congruence. Then you know that the angles are being bisected. So then you'd have to tell me that's 65. Then you have to solve me for the other angle. You actually had to go through more work. Is it a valid way of doing it? Absolutely yes. Do you want to do it that way? Probably not. Probably not. All right, let's keep going though. And each diagram, ray AB is tangent to the circle at point B. Find the value of x. Now guys, with this one, just like the other one, I still have to mark up my diagram. In fact, it's just as important or more so. Because do I still form a right triangle because I have that right angle? Yeah. Now I'm looking for the missing side. Here's my question. Can I use a 30, 60, 90 triangle? Can I use a 45, 45, 90 triangle? Can I use trig? What's your only option? Pythagorean Theorem. Now here's the thing you need to remember. What's the length of segment AC? How would you write that? Nope, not 2x. X plus 2. It's the sum of the parts equal the whole, not 2 times the part, right? So we got x plus 2. All right, so now let's use the Pythagorean Theorem. Leg squared, that's going to be x squared. The other leg squared is 8 squared. Your hypotenuse is x plus 2 squared. Now guys, this is where many of you would go wrong on this. A lot of you do not get the right answer here. How many of you, when you see that x plus 2 squared, do not write this down? How many of you said this? Did any of you say that was the answer? Because if you did, you just got it wrong. Because that's not what I'm doing. I'm not distributing. I don't have a 2x where I can square the 2 and square the 4. That's a what symbol between those two? That's an x plus 2. This is what you're doing. You're really going x plus 2 squared. Same thing as going x plus 2 times x plus 2 Guys, I got to distribute. I got to FOIL. And you have to get every part represented. Now I can combine like terms, and I get x squared plus 4x plus 4. Is that a little bit different than x squared plus 4? So all that work is just so I can get this to be x squared plus 4x plus 4. Now let's do some simplifying of this together. I get x squared plus 64 is equal to x squared. Does anyone feel like a little sick to their stomach, like that looks like it might be a factoring problem or something? It should. The moment you see an x squared, you should have that feeling like, oh, this is not a normal straight up equation. So the first thing you do anytime you see a quadratic like this is you move them to the same side. Well, can I subtract x squared from both sides, guys? When I do that, what happened to my x squareds? It's a beautiful moment when that happens. So I get 64 is equal to 4x plus 4. I subtract 4 from both sides. I get 60 is equal to 4x. What's x equal to? There you go. What do you guys think? Wasn't too bad, was it? Now, I actually think B is easier than A was. I think is if you realize, which I think a lot of you do, that the radii of a circle are congruent. So a lot of you know that the length of segment BC is 3, right? Guys, what's the length of segment AC? 10. All right. Here's the only problem. Do I have a right angle in there? Do I need to get a right angle in there? Make sure you put it in the right spot. It has to be the radius at the point of tangency. So that makes this side, remember, your hypotenuse. Now can I use the Pythagorean theorem? Yeah. So now I can go leg squared plus leg squared equals hypotenuse squared. 9 plus x squared equals 100. Subtract 9 from both sides. All right, now I get this x squared equals 91. So like a good mathematician that you are by now, all of you take the square root of 91, right? From square root of x squared. Now, can I have a negative answer here? No. And guess what? Doesn't simplify any more than that. Square root of 91. All right. What do you guys think? Is it real bad? But you have to know it. Here's another thing you need to remember. On the next one, don't forget little things that can make your life easy. For instance, do you guys agree with me that segment BC is 9? Guys, I have a leg that is 9, a leg that is 12. What's the hypotenuse going to be? 15. Triple. So that lets me know the segment AC is 15, but segment AC is also x plus 9, right? So can't I just set them equal? X is equal to 6. Now, you could set it up like part A, but here's the thing. You'd actually have to factor really well. If you're good at factoring. In this case, what saves us a lot of hassle is we know it's a what? It's a triple. We like those ones. Right, guys? Hopefully you guys are getting and finally learning them. All right, last theorem, and we got to fly. So I'm probably going to get through only like 3 out of the last 4 examples. Are you guys okay with that? All right. So I call this the Two Tangents Theorem. Okay, everyone know this. I call it the Two Tangents Theorem. It is a name I made up for it. It's kind of like the Three Bears Theorem. It's Mrs. Gregerson's name. No one else calls it that. Okay. A Two Tangents Theorem in this case is talking about the segment's lengths, and it's the following. If 2 segments are tangent to a circle from the same external point, then the segments are congruent. Now, here's the reason why those 2 segments are the same to each other, okay? We're going to prove it real quick. You just have to watch. When you're working with this, can I draw in the radii to the point of tangencies? Now, isn't this looking very familiar to that problem on the other page where we had the 130 and the 2 right angles? I know those are the same, and I also know segment AP is going to be congruent to itself. So what do I know? I know that triangle PBA is congruent to triangle PCA by hypotenuse leg congruence. Because I have 2 right triangles, the hypotenuses are congruent, we have a pair of legs. Since those 2 triangles are congruent, what do I know about all of its corresponding parts? Yeah, the corresponding parts are congruent. Guys, remember the saying CPCTC? First semester, corresponding parts of congruent triangles are. See you all, it's scary, but it comes back really fast, I know. So the reason why these are congruent, it's because of that. So corresponding parts of congruent triangles are congruent. Plus, darn it, don't they just look like they are? Let's just go there. Just look it. They just look that way. So here in this first example, it says segment HK and HG are tangent to circle F. Notice these are segments that are a portion of the larger tangents. Now, here's the thing we know. Because of this theorem, they're what to each other? They're congruent. So I know that HK is equal to HG. So I can just go 5A minus 32 is equal to 4 plus 2A. Now, guys, subtract 2A from both sides. I get 3A minus 32 is equal to 4. Add 32 to both sides. 3A is equal to 36. What's A going to equal? 12. Are we done with the problem? Nope, we're looking for the length of segment HG. Well, that same as 4 plus 2 times 12. It's going to be 28. There you go. What do you guys think? All right, this next one actually would have a decimal answer if you did this correctly, but it's the exact same process of setting them equal to each other. So we're going to skip it. Is that okay with you guys? See filled in notes. All right, so that you can find that online, but now let's have a little bit of fun. This is not, okay, I'll tell you right now, this is not in your homework, but this is something we as teachers expect you to be able to do. Like this could show up on a test, this could show up on a quiz, such and such. Okay, are you guys with me on this? So what are you going to mark on here? No matter what. No matter what. This might, like I'm telling you, this isn't going to show up on your homework and all type, but I would still expect every single one of you to be able to do this if I give this to you on the quiz next. Or the test, or the final. All right? Because the rule is what I want you to know. It says in here, in each diagram, a polygon circumscribes a circle. Find the perimeter of each polygon. Here's the problem with this first one. I don't know the length of that line segment. Otherwise, I know everything. But the cool part about this is, do I know the length of this segment and this segment? Yeah, they're both what? They're both 6. Okay, if I've used up 6 out of 9 inches, what's left for the next one? What's left for this right here? That's 3. But what do I know about this segment? What does it have to be? 3, because aren't they from the same external point, and aren't they both tangent segments? Well, if I've used up 3 so far, out of the 8 inches, what's left over? This is going to be 5, right? So that's 5 inches. Well, guys, what's the length of this segment now? Isn't that 5 inches? So what's going to be the length of this whole thing? 11 inches, right? So now you can just do the perimeter. Go around and get all 3 sides of that triangle added up. So I get 9 plus 8 plus 11. So 9 plus 11 is 20. Plus 8 is what? All right. Last one. Guys, talk to me. What would I do? Where would you start? Where would you just start playing with it? Hannah, where'd you start? So you went from here to here, right? So 6 to 6. Which leaves this one to be what? That left from here to here to be 4, which means from here to here is what? So that whole side I know is 9. Great. Let's pick another one. Now would I start with the 5 feet? What do you guys think? Notice you start with the portion of it, right? Not the whole thing. So I get here, this is 5. What's from here to here? 5. That leaves from here to here to be, from here to here to be 7. What's left for this segment right here? 4, which means this one's what? 4. Now do I have all the gaps filled in? Yeah, I know this one is going to be 10 now. Well, let's do the perimeter. Just add up 5 sides of that pentagon, right? So I'm going to start here with this one, and I'm going to go counterclockwise. Why not? So I got 10 plus 9 plus 12 plus 11 plus 10. And you should get with this one, if you did it right, I think it's 52 feet. Homework is from the textbook. Welcome back to using your textbooks. Grade your homework, show your work, you'll all survive.